Monday, February 3rd today. This is CS 746. We're going to do a lecture on data cleaning today. Before we jump into that, though, I want to go ahead and stop for a brief review here. I had some people that were asking, about the questions on the quizzes we've done. So, and this was someone who could not attend class last session. So they asked, can I review the answers for the quiz that we did? So yeah, fine. And it's a simple quiz. How many data types are there? 3. What are they? Structured, unstructured, semi-structured. Pretty straightforward. Okay, which is under structured data? Excel. Tables, text and images are not. Data sets provided for the table are structured data? Yes, they are. Which is an example of primary data? Research paper? No. Data collected from interviews? Yes. Statistics of government reports? Only if the report is about the person doing the reporting, in which case then it's primary. Right? Data from an existing database? That was a joke. Okay, which of the following tools often used for online data collection? Google Forms is the big one these days. Other things exist, of course. SurveyMonkey. All right, that was it. So did anybody want to see any of the reviews for the other assessments that we've done before? Or do you all care? Okay, so hopefully that will be satisfying. I'll check with the student, verify that's what they're looking for. Back to our lecture today. So we're going to do data cleaning, our 4th lecture today. What is data cleaning? Well, it's the process of getting your data ready for analysis, right? You're going to look for errors, inaccuracies, things are missing, irrelevant data, right? This stuff ensures the data set is consistent, reliable, free from errors or inconsistencies, making it suitable for further analysis. So typically, we handle missing values, removing duplicates, correcting formatting issues, resolving any discrepancies that we have in the data. Why should we do this? Well, if you have bad quality data or if you have incorrect data, it will definitely mess up your whole analysis. So you get error-free data, you get better data quality, better accuracy, complete data, and consistency. So make sure that all your data is good and clean. What is our data cleaning cycle? We import the data, we merge the data sets, we rebuild missing data, figure out what should have been there, or determine if we can actually use even that data point or not, right? Because there are ways to fill in, impute values, interpolate values. We standardize the data, we normalize it, we deduplicate things. If we've got data from 2 different sources, right, we can have 2 different sources of data duplication, right? There can just be someone can type it in twice, make an error in entry, and also we can get data when we combine it, we end up with multiple copies. We verify it, we enrich it, we export it to the next stage of our analysis. And then, of course, depending where we are, we may have to be cleaning the data at that next stage, right? Why do we talk about Pandas? Pandas is basically the tool in Python for working with data science, for working with data manipulation, analysis, and cleaning. Python is open source. Python libraries are open source. There are different ways to do data science in Python. There are obviously different languages. R is a familiar example to many people. R programming language is a statistical-oriented package. The interchange between R and Python communities is very strong, but some people prefer one language over the other. So you're not tied to Pandas. It's just, this is what we're going to use in this class because it's easy to work with. And it's very powerful and has an active community keeping it updated. It makes it simple to work with structured and semi-structured data like tables or spreadsheets. So a properly built data frame in Pandas is basically structured data. The cool thing about Pandas is you can give it unstructured data and it will handle it. It won't throw up its hands in disgust like a database will, a relational database, right? You can bring things in, it'll say, don't know what to do with this column, but you can look at it and figure it out and fix it on the fly, right? So it provides tools to perform complex operations. Key components, of course. Rows represent individual records. If we've got grade information or location information about people, for instance, these are the people it represents. The columns represent the fields about those things. So they're ID number, their name, their age, the city they're from, and so on, their salary, so forth, right? So it looks a lot like a spread or a database or a spreadsheet, right? Also, we have indexes. All of our rows and columns in Pandas have numeric indexes. We can refer to them in the column by basically the header, what the name of the column is. We can name the rows, right, with strings, or we can use the default zero-based indexing, right? So we're going to handle our tabular data. There are two primary data structures. There's the data frame, and there's a series. So a data frame is a two-dimensional structure similar to an Excel spreadsheet, where the data is stored in rows and columns. A series is a one-dimensional array-like structure. In fact, a series is a column in a data frame. You go find the Pandas documentation. It's buried down in there. It's a one object nested in another there, right? So we use this for storing a single column, or if we're thinking about it differently, we can, column of data, or we can think of it as a row, depending on how we're treating it in that case. But generally, we think of a series as a column. It simplifies data cleaning and preparation. You've got easy things to do. If you've got missing data, there are methods called fill NA, where not NA means not a number or not available. Drop NA means just throw it away, right? We can throw away duplicates with just drop duplicates. We can standardize and correct data types. So if we have some numbers that are integer and some numbers that are floating point, Pandas is not automatically going to promote everything to a floating point number. Actually, it might, but we can actually take it then and turn it and truncate it all down to an integer, right? Or date time. If we get information in that says in a date time format, but it's not standard, we can tell it to say treat this information as date time. We can tell it how to parse it, or we can actually use heuristics. And of course, replacing, rename, or transforming your data values flexibly. We've got efficient data manipulation. We can do indexing and slicing, so we can chop out the middle of our table. We can chop out certain columns, right? And of course, we have to do that. If we're going to do a linear regression, we choose one of our columns to be the target variable, the other columns to be our free variables or our features, and we're predicting how well those features. We're asking our model tell how well those features predict the target variable, right? So df.lock row column will give us a specific row or column, or we can give it the numbers, so the row index and the column index. Again, ilock for use indexes, and lock is just use the name associated with it. We can apply conditions. So if we say I want to get the data frame of the column of this particular column, right, and I want to get only the things in there where the values are bigger than 50. So I can just chop out everything. It'll just do that as a very simple, straightforward operation. We can do aggregation and grouping operations by using the group by method. And all of these are listed online on the documentation. It's got data transformation. You can merge data sets using .merge or .join. You can concatenate data sets either horizontally, one on top of the other, by adding new rows, or vertically by adding new columns using .concat. We can reshape your data. You can use methods called .pivot table, .melt, .stack, .unstack. Some of those start to sound like good band names. Pandas .melt. Yeah, that'd be a good band. High performance data processing. It's built on top of NumPy. NumPy is the basic math library for Python. So it's got a lot of efficiencies built into it. So Pandas handles large data sets, and I'm going to put quickly in quotes. Quickly, given that it's Python, given that Python is an interpreted language, right? You can always do it faster if you use a compiled language that drops things straight down into machine code and goes to bare metal and all that stuff. You can always find things that are faster than Python, faster than Pandas, but they're not as easy to understand. They're not as easy to fix. They're not as easy to work with. Pandas has that combination of ease of use and speed, right? But some of the class in here, we get into some of our data sets later on, we start doing some visualizations, and you'll see it actually isn't like blazingly fast in all situations. And And we don't have to use explicit loops on our data sets, again, because Pandas does list comprehension, or Python does list comprehension, can do slices, things like that. You can build in the loop and say, I want to work on all these things like this, and it'll just go find them automatically. You don't have to, say, count through every row in the table or whatever. It's integrated well with other libraries. Matplotlib and Seaborn for plotting. Scikit-learn, TensorFlow for machine learning. There's libraries in Python already out there available to use. Many of them included by default when you already installed Anaconda, so your tools are already there. Others you have to download, and that's just a matter of a few minutes to do that. Storing your data, basically serializing, deserializing your data. You can write your data from your program out to a comma separate value, Excel spreadsheet, SQL, JSON, Parquet, whatever. Then you can take your data and input and output. So if you've got data coming from a web page where they've stored it as a comma separate values file, it's easy to import it. Right? And you can export it back out, CSV, Excel, whatever. Right? So there's multiple different ways to import and export your data. It's good for handling missing and inconsistent data. Of course, we already said fill NA, right? Or drop NA. Well, we can also fill NA, sorry. So for instance, if we have some information that's supposed to be, the price of a house in a city. Well, if we have missing data, maybe we really, don't need to worry about it too much. Maybe we just go out there and say, fill in the missing values with the median house price for this city. And it'll let me at least get to a level where I can do some basic analysis, right? It might not be strong enough to actually have data that's useful for doing real work, but it's enough to get a feel for how the data looks. So you can fill in with the mean, median, so on and so forth. Again, we can identify missing values using .isNull. We can standardize inconsistent data formats. Some people write dates as, month, day, year. Other people write it as day, month, year. Those of us that are in the know that the only correct way to write a date is year, month, day, because no one says the time is 37 seconds and 14 minutes before 2 o'clock, right? We all say the time is hour, minute, second, so we should do the same thing with the date, right? That's my soapbox. That's a joke, mostly. We can go ahead and bring up a nice real Python lesson on using data cleaning with Pandas and NumPy and doing it in the Pythonic way. Again, different languages have different idioms, ways to do things. Python says, keep it simple, keep it clean. Here's ways to do it. So there's a good course out here, that a good web page you can read on this. You can also go to right, the Pandas pydata.org. You go out here to PyData, and you just dive into Pandas, and you can search for API, the user guide. If you want to search for, fill NA. There's our different types of Pandas series. Fill not a number of values using a specified method. Tells us all the things we can do. Where it will keep it when we're done, things like that. So all sorts of good information out there. That's an easy to use syntax. We want to load a CSV file. We say df equals pd.read CSV. This will create a Pandas data frame. It will read the comma separate values file into it. It will, use heuristics to determine whether a header is on there. It will determine the types of the columns as best it can. It will plop it into this data frame. Done already. We can find the rows where the column age is bigger than 30. Again, filtered data frame. We take the original data frame, we take out the age column, we find the values that are bigger than 30. We can calculate the average value of a column. So df subsalary.mean. Everything just kind of flows nicely into the next method, simple object-oriented programming. A data frame is a two-dimensional tabular structure. It's similar to a spreadsheet or an SQL table. Of core data structure in Pandas and Python and R. We've got rows. Again, a row represents individual observations. A column represents the features that have been observed at that particular observation. The data is heterogeneous, unlike an SQL table. You don't have to fit into the schema. You can have different types of data in your column. You can have integers, floats, strings, or objects, right? It will give you the lowest hierarchy, or highest if you prefer, in the Python data type hierarchy. So for instance, if you have a column that has numbers and strings in it, and you look at Pandas and you ask you what is the type of that column when you've read the data, and it will tell you it's an object, because strings and numbers are significantly different, right? Rows and columns are both indexed and listed or labeled, right? So you can either access them with integers, iloc, and so on, or you can use the labels, which is more intuitive for most people. You can slice, you can filter, you can aggregate, you can merge data in a data frame easily. Creating data frames, there are so many different ways to do this. Over here, we actually have a IPython notebook, which we created, that shows several of the different ways to create the dictionaries, from the lists of arrays, from the dictionary series, from the dictionary of dictionaries. Someone will go through these just now, but you can go ahead and download this after class, once I remember to make it visible, because I forgot to do that. I make the slides visible? Oops. Pause. I apologize to people that might have tried to download this already. Now it's visible. All right, so here we go. Data frame. We've got an ID column, we got a name column, we got an age column, a city, a salary column, right? So, and again, these IDs are numbers that the person collecting the data assigned to it. The actual indexes are 0, 1, 2, 3, 4, 5, because everything starts at 0 in Python, or in computers that are properly done. And our data frame, once we import that, looks like this. And you can see this is a nice clean data frame. It's clearly a string, that's clearly an integer, so on and so forth. The data frame can be created from a dictionary of lists and arrays. So data is a dictionary, right? Each key in the dictionary becomes the column, and each value in that list becomes a row in that column. When we print that data frame out, and we'll see that output. We can actually use a dictionary series. So we create some Pandas series, right? Alice and Bob, and the indexes on that are 0 and 1. And we can create another series for the age. We'll have 25 and 30, and the index is 0 and 1. We can actually rearrange those indices. We collect the data in different order, and then we'll sort them correctly. So if I had 30, 25 and a 1, 0 here, it would do the things in the same order. I can handle, oh no. Okay, that was an accidental press of the end button. There needs to be a back button, back wherever I was. Okay, so dictionary list, dictionary series. We can do dictionaries of dictionaries. Again, we can have row 1, and then name is Alice, age is 25. So, we're basically saying we're pulling this in. It's going to read this in as the columns are going to be called row 1 and row 2. Then we just do a capital T, which stands for transpose. It'll flip the whole thing about the corner and turn it into a kind of standard data frame. We can use a list of lists. So the data is Alice 25, Bob 30. You can see they're surrounded in brackets outside. So when I create this as a data frame, I can see this. Let's go back to our data cleaning here from a list of lists. Use a list of lists here. And I've got Alice and Bob. Here's where I've transposed the thing. The next is I'm creating a data frame from a NumPy array. So a NumPy array is a n-dimensional array that handles missing values, things like that. So here's our NumPy array 1, 2, 3, 4, 5, 6. If I create a data frame, I label the columns A, B, C, and you'll see that I get those things pulled in there. As the outer is the rows, the inner is the columns here in this case. Here we can create the data frame from a comma separated values file. I think we've got another thing to go to here. NumPy array, yes, CSV, okay. I got ahead of myself. So I have a iris data set. We'll see this more in the class. The iris data set is a classic data set in data science. It was collected back in the 1930s, and it's just a basic data file. Fellows went out into a field in somewhere in New Brunswick, Canada, and measured a bunch of flowers. And they created a data set based off that. And so they have an ID, they have the sepal length, sepal width, petal width, and the species. This, for some reason, decided to squish the columns on here, but this is actually, it should be a column up here beside this. And they have Iris setosa down to Iris virginica, and they're all labeled those, so on and so forth. We can create the data frame from an existing data frame. So it's as simple as df.copy. So again, we've got df up here. We just created that by reading the CSV file. We say df copy. Now we have a second data frame. Many operations you do in a data frame don't change the underlying data frame. They just create a new one and return it. And if you don't do something with it, you've just thrown it away. You've lost your work. So be sure to assign it, right? Subset, df.subset, sepal length, sepal width. So here I'm saying I only want those two columns. I don't care about anything else, right? So I've told it to just select those two columns. I can create data frame from Pandas series. So if I create some series, 1, 2, 3, 4, 5, 6, I concatenate them. And I say you use axis 1, so it's going to be vertical. When it does that, if I say axis equals 0, it'd be horizontal. It would be a 3 wide and 2 high. If I create it from scalar values, right? The data frame 5, index range 3, columns A and B. So I'm actually just going to go ahead and use 5 as this default and use the indexes are 0, 1, and 2. I can use a zip object. Zip takes 2 lists and creates a table out of them, basically, right? So if I say data is a zip of Alice, Bob, 25, and 30, it'll drop those into a single and then turn that into a data frame. I can create the data frame from multiple indexes and tuples. Right, so here each of these in the parentheses is a tuple, and there's a square bracket here indicating it's a list. So I've gone ahead and created my data frame in another way. So many different ways to create data frames in series. Right, so subset from a Pandas series. From an external database, there are libraries like SQL Alchemy you can read from a database. You can read from scalar values. You can use a zip object, multiple index, blah, blah, blah. Okay. Okay, now we're done to series. So a series is a one-dimensional labeled array. It can hold data of any type. Generally, the intent of a series is to treat it as a column and do the transformations to turn it into a single type, but that's not necessary. There are ways to use it just, as a holder for stuff. It's the fundamental building block. Each element is associated with an index. By default, the index is an integer starting with 0, but you can customize it to add labels, strings, and dates. Here's my pd.series 10, 20, 30. I'm going to list it as index A, B, and C. So this is series element 0 by integer location, but series element A by location. And it's, of course, just integers down there when I look at that. Let's see. I can store homogeneous data. So I can have 1, 2.5, and hello. You can see it says it's an object. If I run this, here I can change this to 3, right? And you can see the data type now is float 64. That's the lowest level data type that encompasses everything, right? So we have, yeah, series. We can lists, arrays, dictionaries, scalars. So here again, we've taken a series. We're starting with a dictionary, and we're telling it to build a series out of the dictionary. We can do vectorized operations. So you can say, print s times 2, and basically that'll print out multiply every value in the array by 2 in a single line. We don't have to count through row by row to do anything, and it'll just output a new series. If I just say S2 equals S times 2, I'll create a new series that I can use for further work. When we have 2 different series, it will find where the indices are the same. So if I create, 1, 2, 3, and the indexes are A, B, C, I create 4, 5, 6, the indexes are B, C, D. It will, and I add those 2 together. You will see that A is not a number because there's nothing in series 2. D is not a number because there's nothing in series 1. But B and C will actually add together the 2 and the 4 and get 6. It'll add together the 3 and the 5 and get 8. So it's not going to just blindly line them up. It's going to literally go out there and try to compare the indices and make sure things line up on the things that you are representing to pandas are the same thing. It automatically represents missing values as not a number. This is a standard built-in data type in Python, which says that if you try to do a divide by 0, this is the result you get. This is how we indicate an error in there. If you do the divide by 0 and catch the error there, right? Sliceable indices, just like data frames. So we can print label sub B by index or by position. We can do column addition in a data frame. So we can add a fixed value. We go down here to df subcountry equals USA. So I've created a new column, and it's just going to add that in there, and for everything, unless I specify for only specific rows, right? We can delete columns. The del statement returns a data frame where we've dropped something. The drop statement, can you drop it? You can drop a single column. You can drop multiple columns. You can drop a column. You can specify in place when you call drop, and that will operate on the data frame, not create a new one. So if you've got a big messy data frame, every time you create a new data frame, you're building up more memory. You're moving things around. So sometimes you want to be able to do things in place, save a little bit of memory. The pop method will pull something out of a data frame and it will return it. Right. So I want to pull something out. I want to work on just that thing. Right. So that's where we'd use a pop. We can use location, iLocation to specify what we want to pop out or delete, drop out or delete. Or we can use column reassignments on there. So for instance, using the delete statement. The efficacy data frame, delete data frame. This will literally yank it out of the data frame in place. Using the pop method, we say country column equals df.pop country, and print. I think we need to do, okay, df.pop does in place by default. So we're working on it in place. We can also do row deletion using the drop method, using Boolean masking, and using ilock for index-based selection. So what does this mean? The drop method says drop index equals 1, and it will find 0, 1, 2, so it'll drop the Bob row, right? Boolean masking says remove the rows that satisfy a specific condition, or in this case, keep the rows that satisfy a specific condition. So here I'm making a copy. df equals df. I'm actually taking it out of there. I'm reassigning it back to itself, right? So, and again, I want the age I want the data frame in which the age column is bigger than 25. So we'll throw away it will throw away Alice, who's only 25 years old. We can also use iloc. If I say df equals df.iloc sub 1 bracket, I'm using a range specifier in here, and that says start at 1 and go to the end. Right? So it's going to remove row 0, first row in the data frame or series. We can use append to add new rows. Here's 2 data frames, and we can just append one right on the back of the second one. So here's 2 different data frames, df and df2. When we do a df append, we've actually created an updated data frame to have a new one. And yeah, okay. We can reindex things. And so, for instance, here we've got Alice, Bob, and Charlie in our database. We tell it our indices are 1, 2, and 3. Now we say df reindex 0, 1, 2, 3, 4. When we see our data frame now, we've added a row 0. We've added a row 4 because we told it, we want to add these things. It has no information to put in them, so we'll initialize them with not a number. Gesundheit. So cleaning data is an essential step. What time is it? 11:45, 41. Okay, good. In data pre-processing, so what do we look for when we have our data? We look for start by looking for missing values, which will show up as not a numbers. We can use isNull.sum and print out. It'll show for every column. It will show us how many missing values are in that column. We can impute or remove the missing. So we can impute with mode, median, or mean. Or we impute with domain-specific values. So, for instance, if we have an age, we want to just tell it initialize with 0. For name, we can put in FNU. There are some students here whose name in the WSU student database is FNU. And there are some other students whose last name is Lanu, which, of course, is a placeholder for, we couldn't figure out what this person's first name was when we were parsing this data in. So his first name unknown. How many FNUs or Lanus do we have in here? Anybody? No? I've had FNUs in my class before. I thought it was a really cool name. And then it didn't take me long to figure out I was misinterpreting that information. Yes. So we can remove columns with excessive missing data. We can say if we have a column that has more than 50%, if our sum of missing data is more than half the size of the column, I can just delete that row, that column, right? Duplicates. If you've got multiple data entry, so put the same data in twice. If you've got 2 different data sources, right? Of course, in a database, you'll see a key error when you've got 2 different values where they try to put the same primary key in twice with different information, right? Pandas will put those into the data frame, and you can find them as a duplicate in a particular column and figure out what to do with it, right? So, but duplicates will distort your analysis. It's a bad thing to deal with, so we want to find the df.duplicated method to tell us where the duplicates are, and df.drop duplicates will throw them away. And again, at this point, you're probably being interactive with your data. You're not just out there writing a code, batch process, set it off to have a coffee, and then come back and it's finished, right? You are interacting with the data, finding out what the shape of it is. Another term, exploratory data analysis. You need to understand your data. You need to understand what the errors are in it. And all these steps here, data collection, data cleaning, exploratory data analysis, fade into one another, right? So, here's duplicates. Monty Forsyth is in there. Well, at least they're in there with 3 identical entries, right? So we can just throw those away, right? We also want to check our data types. We want to look at ensure the numeric data isn't stored as strings, right? So if we do a df.age, and we can set that to a floating point by saying it's as type float. We want to convert dates using pd.toDateTime. We want to encode categorical variables properly. There's a method of coding categorical data that's called one-hot coding. You've got multiple values that it could be, and you create multiple columns in your data frame, and the one that it is, For instance, a car engine, an automobile engine, something can run on gasoline, can run on diesel fuel, can run on electricity, can run on hydrogen, right? So if you were trying to code this, how would you do that? Well, you can create 4 columns, and the one that it's a 1 in that column. Only one of those is the hot one, right? You can use label encoding for your data variables. So you can actually just label it yourself. You can use df.d types to get your data types. You check for inconsistencies. For instance, you can look for inconsistencies in your numbering scheme. For instance, if it goes from 3 to 5 on the same slide, that might be an inconsistency. That's a meta illustration there. So male versus M, 1123 versus the correct 2023.01-01, right? Also 12-hour times versus the correct 24-hour time, right? You normalize your string values, for instance, with string.lower or string.replace. You can use fuzzy matching or difflib to identify incorrect typos in your data, right? So you can clean your strings out. If you've got leading or trailing spaces, you can use the strip method, which will just clean out leading and trailing spaces. You can remove special characters, extra spaces, so on and so forth. Again, case consistency, if you want to convert a column, everything in that column to lowercase. Data frame subcolumn equals data frame subcolumn dot string dot lower. So actually replacing that column in the data frame in place. We can check for irrelevant or redundant. Actually, I should point out, Pandas is changing all the time. This is actually something that now generates a warning when you're like updating a data frame in place, a single column, you get a warning, but it works. In the future, they might make that break. In the past, it worked without any complaints. But people were confused. There were errors in their analysis, and the people at Pandas says, okay, we need to make this more clear that something is maybe not doing what you're expecting it to. We want to look for irrelevant, redundant columns. If it doesn't contribute to the analysis, IDs, timestamps, the IRIS data set has an ID 1 through 150 on everything. Those are not really relevant to the analysis, but they do cause funny errors that we can see as part of our examples. Right? They are highly correlated with the others. We use correlation matrices to see if we've got variables that are basically saying the same thing. So, for instance, a person's height and weight tend to be strongly correlated with each other, right? Things like that. Certain constant values, if you have something, the classic example, number of teeth, most about the same number of teeth, either 28, 32, some number between, depending on how many, wisdom teeth you had removed. Children have different numbers, right? For adults, number of teeth is basically a constant. Or if they have no meaningful information, if you've got a column, if you've got a column that's all not a number, or mostly not a number, it's not contributing anything to your analysis, so you can throw it away. We want to validate our data against rules. So for instance, your age. If your age is less than 0, it's clearly wrong. If your age is greater than 150, it's probably wrong. I intend to live that long. We'll see. No, that would be great. But no, your body mass or body mass index. This is a measure of, of how heavy someone is relative to their height, right? And there are values below which you would be dead, and above which you would be unrealistically large to the point where no one is actually get that. So if you see one of these values that's outside of this range, it's an error, right? Unique identifiers. If we have customer IDs or something like that, right? And they're supposed to be unique, we should verify that we don't have the same ID with 2 different names for the customer, right? Referential integrity. We've got foreign keys out there. We want to make sure that those are valid relationships, right? So you can have secondary foreign keys in your database. And Pandas will handle those, but it's your job to find them and fix them. Scaling issues. Some AI machine algorithms require things to be in a standard scalar format. For instance, if we're trying to do certain tasks and we look at height and weight, one is scaled according to inches or centimeters, the other is scaled according to pounds or kilograms, right? If you try to do some of your algorithms, you will find that it will weight the one with the smaller units higher than the one with the larger units. So you rescale everything. So it's a standard normal curve, right? Distances, if you've got some distances measured in kilometers and some distances measured in miles, you don't have valid measurements. You have to convert to one or the other. Kilometers is the correct answer. Actually, nautical miles is what we should all be doing our measurements in. Yes. We should address the imbalanced data if it's applicable. So if we have a target class that's imbalanced, we can use oversampling, undersampling, or generating of synthetic data to fix our imbalances. We need to handle multicollinearity. Well, I mentioned collinear correlation. If we've got things that are highly in lockstep, then having the second one in your model doesn't contribute anything over having the first one, right? So when you have a high correlation, you want to, figure out some way maybe we remove the redundant features to avoid our multicollinearity. We want to convert date time format to ISO 8601. You can use whatever format you want to. I'm going to use ISO 8601 because it is the one true date format. We want to extract useful features like the day of the week, the month, the year, the so on and so forth. There are some trends that vary on whether it's a weekday or a weekend. And so when you get a date, you need to figure out what kind of day was that? Was it a holiday? Maybe, right? Was there an event that occurred on that date in history, right? So on and so forth. We can look at elapsed time between two dates by doing the subtraction on our date times, right? It turns out that measuring elapsed time without the proper tools is quite difficult, right? When someone has their first birthday, they've already been alive for a whole year. And then we go around saying they're 1 year old, but they're 1+ years old, right? So, yeah. I understand in China, the convention is to say when you are born, you are now a year old. You're actually 9 months probably by one measure, but whatever, anyhow. So, true, false? I mean, someone can tell me. I know someone I can ask and verify that. Yeah. We can handle categorical data. Again, categorical data it's just labeled. It doesn't tell us enough about it, right? So we want to go out there and use what we call one-hot coding using pd.get dummies, and we'll create one-hot coding just on the fly for us. We can label that encoding for ordinal categories, which we'll see what those are in a bit. We can ensure the categories are consistent across our data sets. We can check our data set size. If you go get a data set that you are all ready to work with and you find out there's 250,000 records in there, then maybe doing it on your laptop in Pandas, I'm sorry, 250 million records, right? It's fine if you can handle several thousand records. When you start going to several million records, something like that, you're going to need a bigger machine, right? Consider sampling if the data set is too large, right? So sample it just to get your stuff started, right? We need to document your assumptions. This is, again, metadata. It's so important when you make assumptions about your data, when you do cleaning things on there, you need to record what you've done, right? Because you don't want to go out there and accidentally delete, if you're out there looking at the age of employees and you find an employee who's 101, and you say, well, that's clearly an outlier, and you delete it. And then, the next week you find out they're having a retirement party for that ancient 101-year-old employee that's finally decided to retire after they've hit the century mark, right? So yeah, you need to document that step you took during your cleaning. I've cleaned out this outlier, right? And assumptions you make about missing values. Am I going to assume to use the means for this analysis? Am I going to throw those lines away and say, I've got now 40 fewer lines than I expected? Whatever. That is our Pandas data cleaning lecture. I believe we are just down here under the sepal link. So we have some more information in our sample here. We are actually going to do some data cleaning on the iris data set. 150 rows, 6 columns. First row is ID, sepal length, sepal width, so on and so forth. Are there any missing values? Not in this data set. It's nice and clean. Are there any duplicates? No, I don't see any duplicates, right? Or I can just say duplicates.sum, right? But it'll just show me if anything is in there. I can say drop the duplicates, right? I now still have the same data frame. If I print it out, nothing's changed. These are basic things you're going to do to any data set. I'm going to look at my types. The ID an integer, the sepal length, width, petal length, and width are float 64. The species is an object, right? Or a string. If there are spaces on the front or the back of the species, I can tell to delete those. There aren't any. If I want to bring it to a lower case, standardize the case, I can just say to lower, and now change the whole letter on every row, right? I can throw the species away. If I want to do some clustering algorithms and see if it can correctly identify the species without knowing what it is in advance, maybe I'll throw that data away and feed it to a machine learning algorithm, right? I can do correlation matrix. I've created a correlation matrix of the sepal length, sepal width, petal length, and petal width. And you can see that everything correlates 100%. These are percentages. Well, sort of percentages. A 1 is a clear one-to-one correspondence. Everything is exactly the same. A -1 is a negative 100% correlation. So if one series is 0 through 9 and another series is 9 through 0, you've got a perfect correlation. It's just a negative correlation, right? So here we got a negative 0.37. And basically we're saying that's, negative 37% sloping down kind of thing, right? So we can get a heat map, tell it to draw with nice colors on there, and tell us where the highest correlations and the lowest correlations are. And of course, highest and lowest are strong correlations. Weak correlation is a number close to 0. Have time to get into that? Yeah, I got some. And we're going and doing several different things here. We're loading the iris data set. We're applying one-hot coding. We're converting this species into data frame. And now if we've got a one-hot coded, we can see a different kind of a correlation where we're correlating with the species on there, right? And apparently we're only looking at encoding species versicolor and virginica on here. We're not using the iris setosa. And I'm down into some slides. There's some stuff in here that's interesting, but it was the GTA created this. And I'm not sure exactly what I'm supposed to say at this point. So I'll just stop talking. Any questions about data cleaning at this point? It's wonderful to be working with other people on this. It's also entertaining because we're doing 2 different things at the same time. And every once in a while, I'm like, I'm not sure what I'm supposed to say here. That's okay. Let's go to Blackboard. First off, anybody online? No. We're going to end recording.